Hey, chemistry. So one of the things that you've probably realized by now that is that geometry matters. The geometry of the molecule helps determine whether it's polar or nonpolar, what kind of intermolecular forces it's going to have, and even if it's nonpolar, the strength of the dispersion forces based on the size and geometry of the molecule. So it's probably pretty important to be able to figure out, well, what is the geometry of a molecule going to be? Can you make some predictions about that? And that's where VSEPR theory comes in. So VSEPR, or VSEPR if you will, stands for valence shell electron pair repulsion. And it's the key to understanding molecular geometry. So the geometry of a molecule is based essentially on the repulsion that electrons have to each other. Electrons will repel each other and try to push as far away from each other as they can. So knowing where the bonding pairs and where the electron lone pairs are will help you determine the geometry of that molecule and whether or not it's going to be a polar or nonpolar molecule. So as we look at that, let's get some terminology down. So first of all, there's something called a steric number. A steric number is representing how many directions in space a molecule has. So we're going to use a model in which we basically have generic letters that helps us build what this molecule will look like. So the generic letters that we're going to use is A, that we're going to use for the central atom. X will refer to a bonded atom, so where a chemical bond is going to occur, and E is going to refer to the electron pair or the unbonded, the lone pairs. So we sometimes call this the AX method for using these symbols A, X, and E. So again, the steric number is defined as the number of directions in space that leave from the central atom. So these could be directions that bonds are going in space and the lone pairs, because remember, lone pairs take up space and repel the other electrons associated with bonding. So you have to include them when determining the steric number. Then, once we have looked at where things are going in space, we can describe it with a shape name. We can say that this molecule has this shape based on how many electrons they have as lone pairs and how many electrons they have as bonding pairs. Here's another rule of thumb that helps us figure out like where the electrons and bonds are going to go. Lone pairs repel more than bonded pairs. So lone pairs are going to push things out of the way with a greater angle than chemical bonds do. So when you're trying to decide where to place the lone pairs that an atom may have, you're going to try to place them in the location that allows the angles to be as far away from each other as possible. Okay, so what I want you to do is get out a sheet of paper, or you can access the file that I've placed on the Google Classroom. And I want you to make this chart here. And what I want you to do with this chart is we're going to use this chart to determine the geometries of different molecules. Along the top of the chart, you're going to put the number of lone pairs that that atom has. So it's 0 lone pairs, 1 lone pair, 2 lone pair, 3 lone pairs, or 4 lone pairs. 4 lone pairs is a noble gas. That's as many lone pairs as is possible. Going down the line, we're going to have steric numbers. So steric numbers are the number of directions in space things leave from a central atom. So you can have 2 directions in space, 3 directions, 4 directions, so like carbon. And then I want you to put 5 and 6 as well, because we're going to see, as you have already in a couple of examples, with hypervalency, that things can go in 5 or 6 directions in space. So I want you to make this chart so that you can follow along in the next few videos. Okay, so let's start with the simplest example, and that is steric number 1. Now that's not on your chart, but it's pretty simple. If things are going in just one direction in space, it's going to be linear. It's going to make a line. So for instance, an example of something with a steric number 1 would be lithium hydride, or LiH. The lithium is just going to make a straight line bond with the hydrogen. Steric number 2 means going in 2 directions in space. So the AX notation that we're going to use is AX2. So in the box in which something has 0 lone pairs and has 2 directions in space, I want you to put AX2. and then you're going to draw it in the way that I'm going to show you. So something like beryllium chloride would be something that has a steric number of 2. And we would draw its AX notation like this. The A represents the central atom, which is beryllium, and then the X's represent the bonded atoms, which are the 2 chlorines. So there'd be a chlorine here, and there'd be a chlorine here. Because the electrons want to be as far away from each other as possible, they're going to be on opposite sides of each other, 180-degree angle. And so we would draw this as its steric, as its AX notation, and it has a steric number of 2 because it's going 2 directions in space. And this is how we would do a ball and stick model for beryllium chloride. A steric number of 3 with 0 lone pairs. So you could go down the column to steric number 3 directions in space with 0 lone pairs, are going to go in 3 directions that look something like this. So you could have something like boron fluoride, which goes in these 120-degree angles, something like that. You can have, if you double bonded oxygen, you've got a shape that looks like this. And then this other one's hard to see, but also goes in that same direction. So we can draw this as AX3, that would be our AX notation, a central atom A with 3 atoms bonded to it. The example we're using is borium trihydride, so the boron would be here in the middle, that would be your B, and then you'd have an H, an H, and an H. And that would be how we could draw that AX notation out. This ball and stick model shows us there, and then this is going to be bonding at 120 degrees and form a triangle. And so this angle right here is 120 degrees. So it's hard to write, but that's supposed to be a 0, 120 degrees. We call this shape, so I want you to put that at the bottom of that particular box, we call that shape trigonal planar. The reason we call it that is that it makes a triangle, that's where the trigonal comes from, and it's all on the same plane. So it's not a 3-dimensional shape, it's only a 2-dimensional shape. So we say it's trigonal planar, it's a triangle going on one plane. So the AX notation, AX3, the AX drawing, A with the X's going like over here, and then the name trigonal planar. So for every box I want you to put the AX notation, the AX drawing, and the name of that shape.